Galarza. I'm a double E student.
I'm Erick, and I'm also double E.
With Batman and Robin, and we made a digital piano for our CD.
So our system requirements and specific features pretty much is interfacing the keyboard to the Nexus 2, and when pressing the key, that there's like a ankle that sees what key you press and it's gonna emit a sound. And then we use the UART light and an IP port, and then we also have the LCD display that shows what kind of key you press.
Like it'll show the note, like the video will show it. These are hardware and software flow diagrams. These are hardware. Probably recognize this. This is the microwave, OBD, DLNB, VRAM, GPIO, LCD. We're kind of recycling that. What's new is this. The newer light talks to the PS2 keyboard with the baud rate and the modified OBD. And here we actually used another timer counter as a pulse width we made a pulse width modulated signal into our P module speaker. And then we used this timer counter to actually look for the input. We would scan it at a rate of 100 hertz, and then we would see it, we would tell it go over here. And we turn it on, we initialize it, all that good background stuff. And then we start the scanner, which is 100 hertz. They look for the input, and there's no input, it keeps checking, but then after it does, it changes the pulse width modulated signal. It changes the frequency, and it also changes the high time. And then it emits that to speaker. Okay, the new hardware again was just the PS2 keyboard. There's actually 100 keys on it, but we felt the need to only use 49 keys. It didn't take up that much memory. We actually used about 39% of the entire FPGA slices available. The UART light, the baud rate was 9600, but we had to interface that with the keyboard by measuring the keyboard's baud rate, which actually came out to be 11.9K kilohertz. And then using the equation on the blackboard, it told us what the modified OBB clock frequency really needed to be, which was 40.3 megahertz. And then we have a PMOD app 1, we had to buy that from Digilent through their website, and we just plug that in, and we emit the pulse width modulated signal into the speaker through this. And the speaker just is connected, and it makes the pulse to this sound. How do you explain all that? Kind of explain it. The new software was just basically the pulse width modulated signal. Inside of it, the timer counter needs two registers, one to modify the high time and one to modify the period. And every time we call that function inside of our software, it changes it, and then it emits it to the speaker. And this is the status of our project. It's kind of tuned. You'll hear it when we give a demonstration. And ideally, we would have liked to use a DAC, except we had some trouble with the interrupt. With our DAC, we every time an interrupt occurred, it would occur based on what frequency we wanted it to happen. Except we tried using this interrupt as a scanner, so when we change the frequency of the output signal, we would also change the frequency of the scanner, so then some clipping would be going on. So because we couldn't do that, we just used the pulse width modulated signal instead. And now we're going to do the demonstration. Some comments for you guys?
Questions?
Yeah, we're going to hit some keys and you're going to hear what it sounds like. That's the pulse width modulated signal that's really making it sound that way. Play Tetris. Everyone, I think. You guys remember Tetris, right? That old time game too? If I can do it right. Oops. Bear with me.
Let's stick to the
Oh no, it's just a one thing we also forgot to mention is that when we press the key, it shows it on our LCD. Like this key right here, if it was properly toned, it would be a D.
Okay, then you'll see.
Yeah, and then this one would be like the numbers, and these other peripheral keys on the keyboard are the sharps. Not really sharp, but
Sharps and flats.
Yeah.
the sharps and flats.
Do you have any other song in your repertoire?
No. It's not quite tuned well enough, but it's